Alright, can you guys hear me?
네, 알겠습니다.
Can you guys hear me?
Yes,
들려요?
professor.
안 들려?
들립니다.
Yes, professor. 잘 들립니다.
여보세요?
교수님 혹시 안 들리시나요?
저기 목소리 안 들려요?
들립니다, 교수님. 저희 목소리 안
목소리 안
들리시나요?
들려? 뭐냐 이게? 안 되네. 여보, 목소리 안 들려요?
들립니다. 들립니다, 교수님.
목소리 안 들려?
잘 들립니다. 잘 들립니다.
여보세요?
네, 교수님. 저희가 그 교수님 목소리는 잘 들리는데요. 저희 목소리가 교수님께 안 들리는 것 같거든요.
그래?
네네.
그래? 이게 왜 그러지? 잠깐만.
네, 알겠습니다.
내가 좀.
네.
내 저기 그 계정이 웹엑스상에서 사라졌대.
네네네네.
그래가지고 그거 다시 한다고 좀 걸렸어.
네네네.
그래, 이거 좀 할게.
네, 알겠습니다. 네네.
이게 출력이 안 되냐? 자, 목소리 들려요?
저희 목소리 들리시나요, 교수님?
오케이.
네네. 저희도 잘 들립니다. 네네.
오케이. Sorry for the inconvenience. Alright, let's just start. Hold on. 것이지. Okay. Today we're gonna talk about the lumped passive component. Okay. So especially in designing integrated circuit, passive components are very important. So you guys are currently using many passive components, right? Especially for the RFIC, inductors and transformers are very important. So let's go into the detail. So in silicon process, there are several resistors available. Okay, so typically the available resistors are diffusion resistor. Okay, so as can be shown in the cross-section view, so it has a P plus diffusion, and it is typically implemented, inside of the N well. So you have to. It's not option. It's not obligation, but still you have to, uh, you know, use place reverse bias to the NWell. So this is typically connected to VDD, right? So I found that many students in our lab also does not use this external bias, but strongly recommended. Okay, it is because if you place if you bias this into the reverse bias, then this can somehow provide a good isolation from the noisy substrate. So typically the resistor are expressed in terms of resistivity, right? Resistivity and width and length, right? So basically R is 1 over sigma, and this is the length and width and the thickness. Okay, so you just rearrange this in this way, and it becomes I'm sorry. Yeah, it becomes length divided by width, right? So here, this is our resistivity. So this is a resistivity expressed in terms of ohm, right? This is ohm, and this is a ratio. So once you know the resistivity, so this is ohm per scale. So once you know this resistivity, right, you can just synthesize what the resistance value of what you want, right? So the ratio of this, right? So make sense? Okay. So also you guys need to memorize the ballpark number of each resistive layers, right? So typically we use polysilicon, which is ohm per scale, 5 ohm per scale. So let's say you want to implement a 50 ohm, then length is 10 micron and width is 1 micron, then it becomes 50 ohm, right? So for example, if you implement a 1 kilo ohm poly resistor, then you have to make a very thin and wide, right? But if you implement like this way, this is this good? What do you think? Is this good? This is very bad, right? Because if you draw polyline like this, then actually the resistivity over here must be quite different from the resistivity over there, right? So we need a good way of drawing to make this scale resistivity even, right? So there are several types of resistor mismatch, right? So the reasonable importance of resistor matching is that for most of integrated circuit, we typically implement in differential form. So once, as you know, once there exists resistance error like this, then this might induce loss of uh, common to differential gain. So CMRR becomes very bad, right? So this CMRR is typically if the only mismatch is caused by the resistor, then this becomes delta R, and this is just 1 over Gm plus 2 Rs, right? So once your resistivity is has a big discrepancy, then at least you have to make sure the tail current output impedance should be very large, right? So, however, as the frequency goes high, right, it has a relatively large capacitance, and moreover, for the RF application, this is almost impossible to have a large RS, right? High impedance is impossible. High impedance is impossible because of this, right? Okay, so that's why we need a good matching for the resistor. Unfortunately, the resistor variation is almost 30%. Okay, 3 sigma variation is almost 30%. So even sometimes it's even higher than 20%. Okay, this is actually very very bad for designer to achieve a reliable differential pair. That's why we try to avoid resistor as the direct load. But sometimes we need, right? Sometimes we need. So there are several types of mismatches. One is systematic, uh, mismatch. So for example, the contact, may cause mismatch. Also run-to-run variation due to the process variation. And also there exists a random variation because human beings are making those, right? That means there should be certain amount of, undesirable things happen, right? So, which is called as random variation, okay? So never ever try to, use a register as a direct load or just, used for the filter time constant. That's very bad because it varies quite a lot, okay? So we typically use, ratio, just a ratio. Let's say even though, your process has a relatively large variation in this structure, right? It doesn't matter if, those two are crossed together, then, even though it has a variation, V out is same with this. Right? So the ratio is the same, right? Let's say it varies by 1.2, 1.2, just to cancel out. So nothing is changing, okay? So therefore, with a careful, layout and by using the ratio the, circuitry, then you can achieve a 0.1 to 1% of matching, Okay, here is the register layout. So for the large layouts, right, we've seen that for example, 1 kilo ohm poly resistor, right, we requires 20 micro by 0.1 micrometer. In this regard, by meandering like this is one option, but it's still, let's say this is input and let's say this is output, and there exists a large long distance, right? This is separated, which means uh, the variation, there should be resistive variation throughout this path. Okay, so to avoid this kind of problem, we just use this type of structure. Then even though there is some certain amount of resistive variation, right? Resistive variation, it is a symmetric, right? So, overall, between this and this, the thermoelectric effect is, reduced. Okay, so we just that's why we just gather input and output together and route like this. Okay. So also, more importantly, especially for the register layout, we typically need a dummy registers like this. Okay, those are all dummy register, as can be seen here, right? So we have two registers, right? R1 is this, and R2 is this. R2 is this, right? So we have R1 and R2, R1 and R2. Also, there exists the dummy pattern. Okay, this dummy pattern is quite important because once there exists the dummy, right? So the effect, I mean this dummy will prevent drastic changes of environment around this register. Right? If there is no dummy at all around this R1 or around any edge of those two registers, then the values could be changed, right? Changed. So we have to put some dummies around the edges, right? It's important. Okay. So the thing that you have to keep in mind is that once you route any long routing register, right? This can be acting like a RC distributed RC network. Okay. Let's say this is a positive and this is a negative terminal, and the register is distributed like this, right? And also there should be capacitor in parallel, which are distributed all over the place, right? So this is looking like a diffusion equation, okay? So if you express this diffusion caused by distributed RC, the y parameters is y parameter per length is given by this, okay? So this is a the diffusion caused by the diffusion, right? So if you draw this register as a function of frequency, right? Then as can be seen here, right? At 2 gigahertz, right? You can see the register value is here, right? You can see at 200 megahertz, it is around 900. However, as the frequency goes higher, right, at 100 gigahertz, 1 gigahertz, right, it is barely around 500. So there exists a large dependence or depending on the operating frequency. All of them are caused by distributed capacitance. Okay. So for example, 10 kilo ohm resistor drops to 5 kilo ohm at 1 gigahertz with a width equal 5 micrometer. Okay. So this is also if you increase the width, right, then your capacitance value will be increased quite a lot because this is just silicon, and this is a width, length, and this is a distance between the layers and the bottom layers, okay, which is substrate to the register layers. So if you increase the W, your register is also inversely proportional to this, right? Which means the RC constant is reduced quite a lot. If you just if you increase the width, right? If you increase the width, then C is increased and R is reduced, right? So because of this reason, if you take a look at the resistance value as a function of width, it will affect quite a lot, right? So do not try to, make a long routing line, and also do not try to make a long route line with a wider width. Fortunately, in current, DRC rule, it prohibits for the designer to, make such a silly, layout. Okay, it gives a warning. Okay, so you don't have a, chance to use such a wider, register in real world. Okay. Okay, so in CMOS, specifically in CMOS, in standard CMOS, the register size, the area was area occupancy is the money, right? In integrated circuit, right? So as can be seen here, right? The register itself is a very area consuming component. So it can be said that register is very expensive. Okay, so sometimes when you bias, let's say this common source device, right? We have to put the register, right? And we just apply, uh, something like this. This, right? So this is typically, this is a VT track, right? VT track, and this is VGG to bias this, right? Sometimes, if you want to make those circuit very compact, people do not use this, register. Instead, people just try to use, device, just operating in triode. Okay, so I want to talk about it later. Okay, so there are several non-idealities, as I mentioned before. Run-to-run variation temperature coefficient is very high, which is a strong function of temperature, and voltage coefficient is also non-linear. So non-linearity is marginal. Still, this is good factor, right? So especially this voltage coefficient is one of the advantages over this FET register. Okay, so we may just say if you can avoid the polysilicon-based register, try to avoid. Okay, especially in critical areas like amplifier, feedback network, electronic filters, and AD converters. If you can avoid, just avoid. Okay, but if you cannot avoid, you just need to use the ratio, the resistive network. All right. Also, you can use, the MOSFET as a variable resistor, right? Those are very, uh, fun, basic, information, right? So in triode region, right, ID is given by this, right? This is a very well-known, scalar equation. So for the small signal resistance, you just take a derivative with respect to ID with respect to VDS, right? Because VDS is just this, right? VDS is this, which is just this is a main signal path, right? So in this regard, 1 over R is given by this. So R is given by this, right? So here we assume that if VDS is small, then we just neglect this, right? So from this, the voltage coefficient, which is a function of VDS, is just take a derivative R with respect to VDS, and you just normalize it with a given resistor, right? Then you can just easily show that this is a VGS minus VTH minus VDS. Okay. So as can be seen here, right? This voltage coefficient is a strong function of VGS and VDS, which is not good for actually, precise control of any, uh, register. So let's take a look at the application. So MOSFET register is just given by this, right? When VDS is small, VDS is small. So if you want to implement a 1 mega ohm resistor, then you just put the values like this. This is typically 100 micro ampere per volt scale, and you just put 1 mega ohm here, and VGS minus VTH is here in this application. Let's say this is 2 volt, right? Then double over L is 1 over 200, which is a very actually small device, right? So length is a very long, and width is a very narrow, right? So voltage coefficient with a VDS equal to 0 is this, which is quite large actually, right? So anyway, as can be seen, in order for us to achieve a 1 mega ohm resistor, this is insane. I mean, the aspect ratio is insane, right? So how can he achieve a, mega ohm range resistor with a, uh, FATs, right? So there is a good way of doing, right? So just, make a V8 source equal to 0, okay? In this case, there is no channel at all, right? This is just a cutoff, right? Then, as can be seen here, right, this is actually acting like a sort of diode, okay? Sort of diode. So, so here R equivalent is a VT divided by I0 exponential VDS divided by VT. And I0 is just mu C ox double over L VT scale and exponential, and minus V threshold and zeta VT. This is just if you operate MOSFET in sub-threshold region, right? Sub-threshold region, your current, I mean, your MOS is just this is actually NPN, right? NPN. Source and drain are P type, and P, the substrate is a P type. Source and drain are N type, and substrate is a P type. Therefore, it's an NPN device, right? Also, since there exists, two resistors. One is a COX, the other is a C depletion, right? Because there is no channel at all, right? So there exists, depletion to body capacitance, CD, right? So the effective, therefore, this is just NPN, NPN, and this is just, voltage division, right? Something like this. Um, something like this, right? Something like this. So let's say this is a VGG, and this is a COX, and this is a CD, then this is VB. VB effective is a COX plus a CD and COX VGG. Okay, so here we just use this as therefore VGG is what? COX and CD plus 1, right? And VB. Okay. So if I express this diode equation, I mean this exactly speak we are talking about the BJT actually. So I0 and exponential and VT and V actually GZ and zeta here. Okay. Then this zeta is what? This zeta is what? This zeta is B is this, G is CDCOX plus 1. If I express this, this is VGG. So I have to express this in terms of no, okay, this is correct. Okay, so VGG is this, right? Which means VB is right. VB is this. If I say this is this, right? Then VB is if I express VB in terms of VGG, this is this. So I put this over here, then we get this result. Okay, here, since this is a cutoff, we just set VGG equal V threshold. Okay, so we got this. Okay, so typically this value is very small, which is 100 nanoampere. Okay, so from the expression of I equivalent resistor, so once we got this resistor, right? Once we got this resistor, I divided by VT is what? This is 1 over R, in small signal. So R is R diode. R diode, right? R diode is I divided by VT. Okay. Of course, if you apply VDS, then since this is connected together, so this is just acting like single diode. So this is why it has. So from the expression of Req, the resistance is a function of L over W, which is the same with the conventional resistance equation. Okay, so here, right? I is double over L, therefore Req is L over W. Okay, but notice that Req is also a function of VDS. Req is also a function of VDS. As a VDS, here, this is a minus VDS, right? Because this is here, right? So it has to be minus. So as a VDS increase, right, it decreases quite a lot. It decreases exponentially. So we have a large amount of nonlinearity, right? Then how can we avoid such kind of, uh, nonlinearity? We just reduce the VDS for each segment, okay? So we just increase, the number of device like this. We just increase number of device. Then total VDS will be same. So let's say in this case, this is VDS divided by 3, VDS divided by 3, VDS divided by 3, right? Therefore, the effect is reduced, okay? That's how it works. And basically, we typically use, two to three number of MOS, substrate or the MOS resistor, because the actually this MOS resistor induce a large amount of frequent noise. Okay? This is better thing, using MOS resistor at the input. Okay, don't try to use a MOS resistor at the input. Okay, like a biasing gate. No, you should not, because it will induce lots of frequent noise, especially for the mixer, right? This is dead. This is dead. If you just use to reduce area, to save the area, instead of using conventional resistor, if you use this kind of resistor at the gate of mixer, you are dead. You are dead, because the induced flicker noise is very, very large and low frequency. And unfortunately, this low frequency flicker noise is actually converted to, your center frequency. Okay, so do not try to use, substrate or the MOS resistor for, mixer or multiplier. Okay, never ever try to use. Okay, so now let's talk about the capacitor. Actually speaking, capacitor is also quite expensive device, especially for MIM capacitor. It requires redundant mask for the insulator. Okay, extra insulator. This is very expensive. However, many process, especially for RF application, MIN capacitors have been widely used. So, also for expensive process like silicon germanium BiCMOS process, MIN capacitor is always there. Okay, so we have three types of capacitors in silicon technology. One is MOM capacitor. Okay, MOM, which is a metal oxide metal capacitor. With some in older days, we say this as a finger capacitor. Okay, because or interdigit capacitor. Okay, because its shape is looking like this. Its shape is looking like this. Okay, this is capacitor. Okay, if the device size, if we want capacitor value as 5 femtofarad, right? The typical process doesn't provide such a small capacitor. Then we have to make like this way. Okay, this is also, sort of MOM capacitor. Okay, how about MIM cap? MIM cap is just a metal and insulate and metal layers. Okay, metal and insulate and metal layers, which is looking like this. Okay, so it's between two metals, high dielectric material layers are sandwiched. Okay, this is min cap. How about MOS cap? Typically for the metal oxide semiconductor device, right? This has a very good characteristic of capacitor, right? So if let's say this is a prep band, V prep band, right? And let's say this is a V threshold, right? V threshold. So when it is higher than threshold, capacitor is large, and so it's something like this, right? Something like this. Okay. So here, this is C ox parallel with a C depletion, and this is a C ox. This is also C ox. We typically operate MOS capacitor in like this way, VDD, and we place a MOS cap. So this MOS cap is applied, the gate of MOS cap is applied at this. Okay, so if you want to use PMOS MOS cap, then it is operating at accumulation. Okay, but we just make sure that this applied voltage is higher than threshold voltage. Otherwise, this is a strong function of applied voltage and is very nonlinear. Okay, it will induce large amount of AM to PM distortion in your circuit. Okay, so always make sure your MOS cap should not be directly used as a load capacitor. Okay, this is very important. So here, this is a typical structure of MOM cap. As I said, it has an interdigit structure, right? So this is a let's say positive terminal, and this is a negative terminal, right? So when you use MOM cap, if you just look at the cross-sectional area, cross-sectional view, it is looking like this, right? So typically, this MOM cap has a large amount of capacitance density with a fringing capacitor as a stray capacitor, stray or fringing capacitor, right? Those capacitors are very important. Unfortunately, if you have multiple layers like this, then you have a substrate, and there exists a large amount of capacitor between this bottom layer and the substrate. This is a killing point. So once you model this, it is looking like this. Okay, this is what you want, desired. This is a parasitic CP caused by this, bottom metal layer to the substrate. If once it exists like this, then the problem is, let's say you want to implement, capacitor bank, C bank, right? If you want to implement a C bank, right, you just place a MOM cap CD here, and this is a switch over here, and let's say this is a CD here, right? And we just place this like this way. Let's say multiple numbers of, if we implement like this, right? So for this is called as a capacitor bank. Unfortunately, if you take a look at this, if this is on, then this cross, right? So switch on, then it forms like a CD over half, right? So let's say this is a 2 CD over half, this is a 4 CD, then it is a something like binary code, right? Binary capacitor bank. Unfortunately, once you have this CP over here, CP over here, the controllability is that, okay? Because of this CP, whether you turn it on or off, there still exists a capacitor. This is very bad, right? So, especially when you design capacitive bank, you need to reduce the CP as low as possible. How can you make a CP as low as possible? We just remove this. Just use metal 3 to, let's say, metal 9. Do not try to use metal 1 to metal 9, okay? Of course, this is a smaller density, okay? Smaller density. Density will be reduced, but if you implement capacitive bank with a high CP, then you will lose your controllability, okay? So whenever you try to design any capacitive bank, do not try to use M1 and M2 at least. Sometimes I remove M3 as well, okay? Remove it to reduce this CP. Okay, there are several, way of implementing high density MAMCAP, okay? So most widely used is parallel stacked wires, which gives the highest density and smallest, good routability, right? Right, routability is also important, right? However, as can be seen here, except the MIM capacitor, all of those MAM capacitor has a high CP, okay, high CP. Okay, you have to avoid, by chopping off, bottom layers. Okay. So this is a MAM capacitor, MIM capacitor, which is an expensive capacitor, but has a very, very small, substrate parasitic capacitor, top to substrate parasitic capacitor. Okay. That's why people try to use MIMCAP. Okay. Also, it consumes relatively large area, okay, compared with the MAMCAP. Okay. So this is typically used for, high cost or, flagship application. Okay. So this is a MOSCAP. Okay. As I said before, MOSCAP has this kind of characteristic, right? This kind of characteristic. Okay. Let's say this is a V threshold, and let's say this is a V flat band, something like that. Okay. So this MOSCAP, for the MOSCAP, source and drain is connected together. Okay. Source and drain is connected together. And we just apply the signal like this, then from this equation, right? This is applied voltage, AC voltage, and this is a capacitor, and this is a current that that is a measured line, measure the current, then I can get the capacitance value. So you just try to extract, capacitor. Okay, this is a maybe this is a lab 2. Okay, just extract most capacitor characteristic for our design the MOSFET whose size is let's say 50 by 50 micron, or maybe just I don't remember the size of unit cell, but let's say 5 by 5 unit cell, 5 by 5 unit cell, or the 5 by 5 the MOSFET with a 5 by 5 unit cell, just extract C, okay, as a function of a VGS. Okay, this is a lab 2. okay, 알겠지? 여러분들 어디서 extraction 하냐면 40나노에서 해요. 40나노하고 65나노하고. 알겠지? 65나노, 40나노에서 우리 유닛셀이 있을 거야. 거기서 5x5 유닛셀에 대해서 VGS에 따른 캐피스턴스 밸류를 추출을 하세요. 알겠지? 이렇게 나오나? FFSSTT에서 추출을 해보세요. 알겠지? 이 숙제야. 자, alright. So this is a conceptual view of a view of capacitance value as a function of gate body voltage. So this is you guys are very familiar with it, right? So when negative bias is applied, right? So let me just draw like this way. Negative bias is applied, then positive over here, and there exists a polarization, right? So at the bottom of this, at the surface of this substrate, the free carriers, which is a hole, because this is a P substrate, right? Holes are induced over here. Holes are induced over here. Then, therefore, we say, carriers are accumulated. Carriers are accumulated. Therefore, in this operation, we say this is accumulation. Accumulation mode, right? In this accumulation mode, right? So, which exists before the which exists when VGS is smaller than V flat band voltage, right? That's natural, right? Otherwise, once it is become, less than VGB is less than V flat band, then it induces depletion. Okay, so the capacitance, effective capacitance is from this and this. This is a COX capacitor. If VGB is smaller than V flat band, then this area will be covered with actually, the bonded capacitors. Bonded charges, which is caused by the ionized atoms, right? This is not carrier, right? So between this and the bottom, this is caused by depletion region, right? So in this depletion, which is a COX plus C depletion, COX C depletion. And here C depletion is a function of C junction square root 1 plus V gate body and 2 pi b. Therefore, as the VGB increases, C depletion is reduced. Once it reaches to the threshold voltage, naturally it forms channel at the surface. Therefore, you don't see this. We only see this, right? That's why it's looking like this. Okay, so this is the table which summarizes the capacitor options in CMOS process. As can be seen here, if you use a gate MOSFET, right? Definitely, voltage, coefficient is huge. Okay. So, but this MOSFET has the largest, capacitance density. Okay. So, so this is the same, right? It's a bad rush. Okay. But you guys, be noticed that you cannot use, those two as a load, right? Because it is a strong function of applied voltage, right? Now let's talk about on-chip inductor, okay? On-chip inductor. So the on-chip inductors have been widely used in RF application, right? So the biggest difference between analog circuit design and RF circuit design is, the knowledge on the inductor. Okay? Knowledge on the inductor. The analog guys don't know about the inductor. Okay, RF guys cannot make money without inductors. Okay, our RF circuit are typically so simple. Okay, so there are not many things to do. So we have to have a very solid knowledge on the inductor as an RF designer. Okay, especially the most widely used application for the inductor is inductive picking. This is inductive picking. Inductive picking for wideband application. Okay, so by placing inductor in series with a resistor, right? This is generating, with this C, this is generating, Q relatively low, right? So the network Q is just bandwidth divided by, inverse of network Q is bandwidth divided by center frequency. Okay, for a given center frequency, if you want to increase the bandwidth, you have to reduce the Q, right? How? We just connect R in series with R. Okay, so by doing so, you can just can boost the bandwidth by 80%, which is amazingly high, right? So this is the list of common applications of on-chip inductors. Okay, the most widely used is just tuning out the capacitance. Okay, we just tune out capacitance. We just resonate down, right? This is the most widely used one. So for example, this R just resonate down with this cap, and at given F0, which is a scale 2 pi square root of LC, we don't see any, capacitor. We only see R. Therefore, AV is increased quite a lot, right? This is how it works. Another application is this shunt picking, right? As I said before, this forms a low Q network. So the bandwidth is increased. Bandwidth is increased, right? Bandwidth is increased. Okay. So also, inductors have been widely used for the matching network, right? We just implement LC, L-type LC network, like this or like this, right? Or like this, or like this, right? Okay. So here are the inductor performance metrics. Okay. As I said in R and C, the occupancy, area occupancy is the money. Okay. So we have to reduce Ln, the size as small as possible. But there is a problem. Okay. In order for us to increase the inductor line, what is inductance for the spiral inductance, right? For the spiral inductance, how it works? Inductance is actually, number of flux line. This is a flux linkage line. Flux linkage is a number of coil, and this is a magnetic flux line divided by I, current line, divided by current. So let's say this is just a solenoid, something like this. Okay, for the solenoid line, B or B solenoid is given by mu, right? And let's say this is the length of L, and number of N, right? And also, if current I is conducting, then it's looking like this, right? This is a well-known solenoid equation. Okay, so what is pi m? Pi is just the area of this line. Area of this. Let's say this area is A, right? Then this is just a mu n l a, right? Also, since there are number of n's, right? Because we are talking about, we don't talk about a, right? We have a n number of a's, right? N number of a's. Therefore, in terms of linkage, right? This is a number of a, right? This is a linkage. Okay. Therefore, L is given by L mu a n square. Okay. This is a typical inductance relation. So in order for us to increase the inductor line, we have to make a very dense coil with a high area, right? And we should increase the number of inductance, number of winding. Also, we have to use core metal with a high mu, right? High permeability, right? That's how we make a high inductor in discrete form, right? But there are so many problems in implementing high inductance in on-chip, right? First, you cannot arbitrarily choose number of n for a given area. If you take a look at this structure, right? So in order for us to make a routing line, longer, lengthy line, we just, made like this way, right? So here, just made like this. This is how many tons do we have? How many tons do we have? How many tons? 1, 2, 3, 4, right? 4 tons. But unfortunately, this is different from this N. Why? Because of the area, right? Area is different. Okay. So linkage is reducing quite a lot for this on-chip structure. Okay. This is problem one. The second problem is since each routing line is crossed together, there exists a parasitic capacitance between each routing lines. Okay, so this will also induce lots of troubles, something like this. Okay, and it also has a capacitance between, this routing line and, the substrate. Okay, so every capacitor, when you route such kind of a spiral structure, result in parasitic cap, which result in lower resonance frequency, which is the problem. Okay. Another thing that you have to consider is inductance. Whenever you consider inductance, you have to always consider return current, return path. Okay, return path. Whenever you think about inductor, you have to think about return path. Okay, let's talk about this. Okay, let's say inductance is placed like this. Let's say this is the inductor. Okay, so throughout this inductor, actually speak, this is a routing line, which is inductor. Throughout this inductor, this inverter is driving this capacitor. Okay, that's fine. What is the problem? You don't know about this inductor line. There should be inductor in the path of current return, right? Return current also meets large amount of inductance. You don't know, right? Where is the routing line? Whether this current is from here to here or from here to here, you don't know. Okay, this is the problem. So whenever you define the routing line, you have to make sure what is the return path. Otherwise, your simulation will be wrong. Okay. In our lab, we always make a solid routing return path by placing, ground metal all over the place, right? By placing ground metal all over the place, right? Since inductance is inversely proportional to width, right? If you make this width very wide, then inductance will be negligible. So we can neglect this. Okay, so this is very solid. That's our design strategy. Okay, and also, you guys typically don't consider the substrate tab, but this substrate tab is also very important. Once this substrate tab is nearby your circuit, it can also partially induce, return current path. Okay. Let's talk about self-inductance and mutual inductance in terms of electromagnetisms. Okay. So the self-inductance itself is just the inductance produced by conducting current in inductor itself. Okay. Inductor itself. Okay. This self-inductance consists of internal inductance plus the external inductance. Okay. This internal inductance is inside of metal that conductor current. Okay. So this internal capacitor is internal inductance is almost zero as a frequency was higher due to skin effect. Skin effect. Skin effect. Okay. So whenever we talk about inductance, we typically talk about external inductance. Okay. This internal inductance is typically 8 pi mu 0, okay, which is quite small, and external inductance. That's what we are talking. Okay. This external inductance is given by this equation. The inductor is defined as linkage divided by I. Okay. So you can easily get the inductance easily from this definition. Also, you know, the easy peasy way of extracting inductance is to use this relation. You just calculate the energy, stored energy, and from this stored energy is given by what? Given by BH EV, right? We just you know, get stored energy from this result. So this stored energy is actually 1/2 of Li square, right? So once you get Wm, then it's easy to get inductance. Okay, that's typically what we get inductor for a given structure. Now, other than self-inductance, mutual inductance is also very, very important, especially for transformer. Okay, the definition of mutual inductance is given as this figure shows. Okay, so it has its own, you know, flux generated by, you know, conducting current. Okay, so this has a conducting current to this. So those conducting current, right? This conducting current, those conducting current may induce its own flux. But if those two are close together, then part of generated flux, actually speaking, part of generated magnetic flux density will go through this second coil. Okay, go through this second coil, which is just written like this, mu12. Okay, mu12. That is defined by B2 integrating through BS1. S1. Okay, something like this. Okay, so once you define flux, mutual flux, then the mutual inductance is mutual inductance 1, 2, which is caused by current 2 and generated linkage at the the first coil, which is N1 and flux 1, 2, right? Okay. From the Newman's, equation, M12 is always the same with the M21, right? So this is also true for any passive component, right? Passive component has a reciprocity except a ferrite bead, right? Okay. So now talk about internal and external inductor, right? So as I said before, the total self-inductance is given by, internal flux, internal inductance plus external inductance, right? So unfortunately, this internal inductance, as can be seen over here, this flux is, ds and b here, right? So this ds is a function of frequency, right? As the frequency goes higher and higher and higher, all the current conducts only at the edge, which is called as a skin effect, right? Skin effect. So as the frequency goes higher, internal flux becomes 0. Okay. So here the internal inductance is, as I said before, mu over 8 pi, right? Which is actually relatively small, right? So as a current distribution becomes confined to the surface, right? So here, the linkage, hold on. So here, right? Here, right? The linkage becomes, the linkage becomes getting small, and it becomes 0. Okay, it's very simple to make an analysis. Now let's talk about inductance model. This is very important. Okay, people are sometimes looking confused. Okay, so the typical on-chip inductor, which is let's say looking like this. This is a port 1 and port 2. Port 2, okay. This is a top view. Okay, let's say this is a port 1 and port 2. Okay, so this routing has an inductance, right? This routing has an inductance, as well as a resistor, right? Resistor, right? This is what we draw. And if you take a look at the cross-sectional view, it is something like this, right? Metal layers and back end of the lines, right? And silicon substrate, right? And this is oxide layers. So oxide layers, it has a capacitance, and there exists, silicon, silicon, and also, the silicon is quite resistive, quite, lossy, right? So we just express the structure like this way. Okay, very simple. So in this regard, you just take out y parameter. Just take out s parameter and convert it to y parameter, and you can easily get the each part, right? For example, y11 is 1. Y11 is v1 and I1 and v2 equals 0, right? Since v2 is 0, we just make it to ground, right? So what we can see is this this structure, right? In the same way, you just extract the y21, y12, so on and so forth. Then you can extract each values from y parameters. Okay. So when it comes to single-ended inductor and differential inductor, right? This is a very informative to the student. Okay, so the inductor can be driven, right? Can be driven either single-ended or differentially, right? For example, you can just drive inductor, right? As we've seen before, this is a inductor, and this model is looking like this. Okay, so this is once this is a single-ended, right? We ground this. Okay, we ground this node, port 1, port 2, ground this node. So equivalently, it's looking like this. Okay, and how about differential? We just excite here, like this. Okay, then what you can see is we have a two resistor and see this, right? See here, connect here, excite differentially. So what we can see is mainly because this is connected together, right? This is connected together, right? So approximately this is those are in series. So we see 2 RP and this, we have a this is in series, so which is looking like this. CP, okay. So which shows this is a CPO2, and directly connected to CO. So approximately, it is looking like this. Okay. So if you draw this as a function of frequency, you can see differential pair has a much, better Q compared with a single-ended structure. Moreover, the self-resonance frequency is almost twice. Okay, why is that? Because you improve the RP twice, effective parasitic resistor twice, right? Because it is connected together, right? And you make a CP almost a half. Therefore, you improve Q. Therefore, you improve self-resonance frequency. Okay. So you have to use inductor in this way. Okay. Whenever you use inductor, you have to operate it in differentially. That's why people are preferring transformers architecture. Okay. And when it comes to shielding, right, it is a, you know, pro and cons. It has a pro and cons, okay? The advantage of this is to reduce, eddy current, which will, improve quality factor Q by 10%, okay? So the way how it goes is to avoid, eddy current conduction. This and this and this and this are separated. Okay, the induced eddy current is, routing going in this way, but because of the metal structure is separated like this, it cannot go through these metal structures. Okay. Also, this shield is applied. If you take a cross-sectional view, then this is a oxide, this is metal, and this is a shield. Okay, this shield prohibit the capacitive coupling through the lossy substrate. Lossy substrate. Okay, so the shield is not for magnetic shield, but for electric shield. Okay, but if you make like this, then what is the problem? The problem is a self-resonance frequency is getting lower. Okay, this is not good for high frequency application. Okay, so for as a terahertz, sub-terahertz or terahertz circuit designer or millimeter wave circuit designer, we don't use this. Okay. Now let's talk about shaping of on-chip, inductor. This is a very clear, right? So as can be seen, inductor is actually length, right? Mu and area and n square, right? So what you have to do is, the resistor is also proportional to, width and length, total length, right? This length is just, since, for the on-chip, we don't have this. Okay? So inductor is just proportional to this. So we want to make this high while we want to make this low. So there is how can we do that? So instead of reducing the peripheral length, we need to increase the area. Which one has the largest ratio between area and periphery, each periphery? This is a circle, right? If you make a circle, the surrounding length is just 2 pi, and the area is actually a pi square, right? So the ratio is just pi over 2, okay? Pi over 2. Let's talk about the scale. Let's say this is the area, this is the area. So the area is the length, okay? The area is a square, right? Total length is what? 4a, right? This is a over 4. A over 4, okay? A over 4. Let's say this is a 1, this is a 1, okay? Then this is a 4, this is a 1, okay? This is the, ratio. So this aspect ratio, this, scale has a better A over L compared with the rectangle, but this is better to, this circle is better than this scale. But, unfortunately, this circle cannot be implemented because of DRC rule, right? So That's why we implement like this octagonal structure. Okay, octagonal structure, which is similar to circle, right? By doing so, we can improve, quality factor Q by 10%, which is a relatively large. Okay, here is the setup of the simulation setup. So if you want to, extract, S parameters, isolation, then let's say the isolation is 50 dB, then this is in magnitude wise 0.03. So in HFSS setup, you have to make delta S smaller than this value. If you just set this delta S less than 0.01, then it's a it's a reliable minimum value is minus 60 dB. Okay, that's how it goes. Okay, so also you should define port very carefully. Also, if thickness is thin enough, okay, which is let's say 100 micrometer, then always try to put the PEC at the bottom. Why? Because our chip is always on top of the chuck, right? Which is just the metal layers. So we have to place the PEC at the bottom if thickness is thin, okay? Especially this is very important whenever you design, on-chip antenna. So this is off-chip inductance, which is typically used in old days, just place on-chip spiral and use those bonding wires as extra inductance. Okay, but unfortunately, if you place a packaging lead line like this is a very, very difficult to control line. Sometimes you may have this amount of area, but another times you may have this amount of area, right? Sometimes your routing line may be like this, so the area is like this. Depending on the closed loop area, right? Your inductance varies quite a lot, right? As I said before, L is N scale A, right? So A. So now let's talk about ideal transformer. The transformer is a device that converts voltage and current based on the turns ratio. So you have a transformer with two coils. Then the first one, once current source is applied, then because of Ampere's law, it will induce flux, and flux is goes through the high permeability metal, and link and forms a linkage with a second coil, right? So the linkage is, let's say this is second coil, then this is like this line. So which is flux 1, 2, okay? So anyway, the turns ratio is here defined as second divided by first, okay? So this is typically used in microwave society, 1 to n, okay? 1 to n. So this is dot notation. So this dot notation tells you the direction of induced the direction of polarity, which was induced at the induced. So for example, if you apply positive and negative over here, if you place a dot over here, then if this is positive and negative to the load, to the road, then you have to place that over here, right? If you apply like this, and if your transformer is looking like this, right? Then it's looking like this is positive right now. Okay, that's how your dot is working. Okay. 여러분 잠깐만요. 이게 다 깨져서 보이니까 이게 좀 깨져서 보이니까 내가 이거를 파워포인트로 만들어서 내가 다시 할게. 한 5분만 기다리세요.
네,
5분만.
알겠습니다.
어, 이제 이거 저들이 Okay, can you guys see? 여기 보이나요?
네, 지금 PPT 슬라이드는 지금 보입니다.
Okay. Right. Let's talk about annotation again. So, as I said, in microwave society, the ratio, transformation ratio is defined like this way, okay? Which is different from the definition in the physics society, okay? Anyway, we use this. So when we apply voltage over here, right? And it will induce the coil is the winding coil is the coil is winded in this way, right? Which means if you see on top of the if you see the side of the coil, right? Coil is winded in direction of counterclockwise. Okay. In this way, due to the right hand rule, the induced magnetic flux is pi 1, which is circulating in clockwise. Right? This circulating magnetic flux will generate, since this is a changing with the time, right? This will induce, the voltage, which is from the Lorentz and Faraday's law. So the induced time varying magnetic flux will go through the area of a second coil, right? Area of a second coil. And since the induced current is opposing the induced flux pi 1, so pi 2 is generated. So to generate this pi 2, which is circulating in opposite, which is in counterclockwise, right? So we just wind the second coil in direction of clock, in direction of clockwise. So since this is in direction of clockwise, in order for this current to generate pi 2, or in order for the induced current to generate pi 2, the induced current is shown to be like this arrow. Therefore, if this second port is connected to the resistor, then the top one is positive and bottom one is negative. So we have to draw that at the top. Okay, so for the bottom drawing, it is the opposite case. Okay, so then let's talk about any way that I can draw. 이게 문제네. 이 그림을 못 그리네, 이게. 그림을 못 그려. Let me just draw. Draw a graph. So let's say we have a routing inductor like this, and we draw another secondary coil like this. Okay, in the cadence. Let's say this is a positive, and let's say this is negative. Okay, which one should be positive?
교수님,
어,
그 화면이 지금 안 보입니다.
안 보여?
네.
아, 맞다. 이 내가 바꿨지. 잠깐만. 보자. 이거를 이렇게 안 하고 이걸 이렇게 하면 보일 것 같은데 지금 너무 늦어 이게 그때. 한번 해볼까 이걸? 잘하면 될 수도 있겠는데. 이렇게 한번 해보자. 그러면 그렇지. 이렇게 하면 잠깐만요. 이렇게 놓고 이거를 이렇게 하나 얘를 공률하기를 공률하면 아이고 이렇게 자, 이거 보이나? 좀 뭐 이상하게 보일 것 같은데 사이즈가 작게 보이지? 어때요? 뭐 볼만해요?
네, 맞습니다.
자 그러면 여기다 내가 그릴게. 자, let's assume 어? 씨, 이래 안 그려지네. 반응이 늦어갖고 그런가? 좋지는 않겠다. 그냥 여기다 그릴게 그냥 여기다가 어쩔 수 없지. 음, 그냥 여기다 그릴게. 진짜 안 커지네. 자, alright. Let's assume we have this typical transformer structure. Okay, this typical transformer structure. 이게 왜 안 되지? 왜 안 되냐? 맛이 갔네. 쉽지 않네. 이렇게 하고. 이제 보여요. 아, 여기는 또 안 되는구나. 화면 턴 터치. 그림을 못 그렸다. 화면 원해. 자, let's assume you draw transformer like this way. Okay. So which one? Let's say this is a primary. This is a primary, and let's say this is a secondary. Which one has to be positive? Which one has to be negative for the second part? Okay. So basically, you just draw this as an equivalent circuit like this. We have to place like this way, okay? So this is positive and this is negative. This is negative and this is positive, okay? This is how we have to achieve, okay? So let's take a look at in this case. Let's say we apply signal over here and current gonna conduct like this, okay? Since the current is conducting, magnetic field at the first winding is generated like this, okay? So to prohibit this, to be against with this, right? The induced current is such a way that it is, against of induced flux. So this magnetic flux will be generated by the induced current. Therefore, the current is conducting in this way. So which one is a positive and which one is negative? This is a positive, this is a negative, right? Because the current is conducting like this way, right? Because of a right-hand rule, this is a flux 1. This flux 1 will go to the flux 1, 2. So to avoid this flux 1, 2, the induced magnetic flux will in this direction. In order for this direction to be generated, right? The current, the direction of, the current on the second winding line is like this, which means positive is here, negative is here. Then it is looking like this. Okay. All right. Also, another important thing. You notice that the inductance is defined even in DC. Okay. Inductance is defined even in DC. Okay. It doesn't matter whether it's a DC or AC. Okay. That's important. And so at low frequency, right? Typically, this magnetic core boosts inductance. However, as the frequency goes high and high and high, right? Then this magnetic core doesn't do much. Also, we cannot use this magnetic core in the on-chip structure, right? Okay, so here are transformer specifications. So the most important one is the inductance, which sets location of 0 in transfer function. And, we need two inductors for the broadband transformer. And second one is a coupling factor. Okay, so if a coupling factor K is higher, we typically use a transformer as a resonance circuit. If K is low, then we use a transformer as pole splitting. As K getting higher, the loss is getting small. Loss. Okay, insertion loss is getting small. So for the pole splitting application, since K is low, therefore insertion loss is relatively high, which is around 1 dB to 1.5 dB. Okay. And also importantly, the important figure of merit is a quality factor. Okay, this quality factor Q1, Q2 multiplied by K defines the efficiency. Okay? Efficiency is just inversely proportional to insertion loss, right? So if efficiency is low, insertion loss is high. Okay, so in order to reduce the insertion loss, we have to have a high K or high Q or high Q1 or high Q2. Okay, so winding resistor, which determines quality factor. Okay, and the minimum insertion loss, which is just calculated by G max, maximum achievable gain, right? So this is a basic transformer model. We typically use 5 parameters. One is L1, L2, R1, R2, K, right? So how about Q1 and Q2? Q1 is just omega L1, R1. Q2 is omega L2, R2, okay? So you can easily extract equivalent circuit, equivalent model, equivalent parameters. Right? We notice that all the values are all the parameters are extracted with the impedance G parameters, not Y parameters. You should not use Y parameters. Why? Why you should? Anyway, once you extract G parameter, you can convert it to Y parameter. Then why not use Y parameter in extracting those values? Why not? We typically use Y parameters. Okay. So as can be seen here, right? So in order for you to extract Y parameter, right? This is a V1, I1, and V2 is 0, right? So for the transformer, right, it is something like this. So in order for us to make a V2 0, right, you have to make it short. That's the problem. If you extract Y parameters, this current will generate, induce the current over here. Okay, so you cannot separate, the value from secondary coil to here. Okay, you cannot separate because it interacts each other. However, if you use G parameters, you can do that, right? G parameters, it is defined like I1, V1, and I2 is 0. Since this is open, there is no current conduction. So there is no induced, magnetic field over there. So you can solely consider the effect of a primary coil. That's why. Make sense? Okay. So we also may use this T model, right? So if this is a positive, then L1 plus this is a positive, right? And this is minus M. This is L1 minus M, right? So total inductance shown at this point is L1. Total inductance shown at this point is L2. Okay. So we notice that this T section model cannot be used for DC, right? This is valid only for AC. Why? Because at DC, there is no interaction at all, right? This is directly open. That's why. But if you just conduct a current over here, at DC conducts here and here, right? So it's different. Okay. Anyway, mutual inductance M is given by K square root of L1 and L2. Okay. So now, let's take a look at, the configuration of transformer, right? So let's consider the effect of a parasitic cap, series parasitic cap like this, right? Okay. So from the, V in, right? V in is what? V in is SL1 I1 plus SM I2, right? V out is SM I1 plus SL2 I2, right? Which is exactly, shown from the G parameters. So we just, from these two equations, you can easily express the I2 in terms of, those V out divided by SL2 minus M divided by L2 and blah, 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 right? So if you apply KCL and replace I2 from this, then you can, express, the transfer function given by this. Okay. It is very interesting that if you put J omega instead of S, right? It is looking like this. Minus L1, L2, 1 minus M square divided by L1, L2, CF omega square plus M, right? Let's say M is larger than 0, right? This is definitely, this is because of minus, right? This is definitely, minus value, negative value. If M is larger than 0, right? Positive minus positive plus negative, or positive minus positive value can be 0, which means, there exists, numerate 0. That means there exists 0. Okay, there is no voltage transfer at all. Something like this at certain frequency f. The signal is something like this. This is very bad, right? We need this kind of, voltage transfer. However, if you set M equal less than 0, which is something like this, right? This is M less than 0, right? Since this is less than 0, this is less than 0, minus plus minus is always minus. It cannot be, it cannot make any notch, right? Okay. Therefore, we conclude that M should be negatively coupled. Okay. M should be negatively coupled. Right? Hold on. Okay, sorry for the noise. Right. So also let's talk about CF equals 0, which is typically valid for maybe up to 20 or 30 gigahertz. Okay, so as can be seen over here, right, you can just easily get the relation like this. Okay, the input impedance is given by this. Okay, once you express input impedance in terms of L1 as well as L2 and load, right? Okay, you can just come to see the required impedance shown at the source, right? Source impedance should be in conjugate, right? Okay. All right. That's actually a concept of matching. Here is the lab 1. I already mentioned about lab 2. Okay, so design 40 pico, 200 nano, and 2 nano. Oh, this is wrong. 200 pico. 200 pico and 2 nanospiral inductors at 100 gigahertz for 40, for 200, for 1 gigahertz. Okay. No need to, design, 2 nanohenry at 100 gigahertz. This is impossible. Okay. Forget about it. Just, for actually, this is respectively. Okay. And present the capture the layouts in cadence and HFSS. Okay. Present the S parameters from point 1 F0 to 10 F0, for example, 10 gigahertz show from 1 gigahertz to 100 gigahertz. Okay. Extract the inductance. Okay. And Q. And present self-resonance frequency of each inductors. And we have another one. Design 1-to-1, 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 1-to-2, 2-to-3 transformer operating at 30 gigahertz. Present the capture layout in cadence and HFSS. Okay. Present S parameters from 1 to 60 gigahertz. Extract those values for the design the transformer. Present self-resonance frequency. Okay. Those will be helpful for your design in the future. Okay. You may just use either 60, 65 nano or 40 nano. It's your choice. Okay. Just show which process you used. Okay. That's it. Okay. This is the same. You may just use 40 or 60. Okay. It's your choice. But just show. Okay. Present which process is used. Okay. All right. Let's wrap it up. Thank you.
네, 감사합니다, 교수님.
감사합니다.